Hello, I am Lakshmi Dikshita. I am explaining my topic. I am from CSC department of section C. I am explaining my topic about Green's theorem. Green's theorem. Introduction to Green's theorem. Green's theorem relates the circulation around a simple closed curve to the double integral over a plane region it encloses. It is a fundamental result in vector calculus linking the integrals of the surface integrals. The theorem is named after British mathematician George Green, who formulated it in the 19th century. Mathematical statement. Green's theorem states that if slash n slash of C is positively oriented simple closed or simple curve and slash D is the region bounded by slash C, then point C dx plus q by dy integral d left fraction q partial x fraction partial p plus partial y right dA. Here slash p and slash q are the functions of x and y that have continuous partial derivatives on the open region that contains slash d. Conditions for application. The functions slash p and slash q must be continuously differentiable on an open region containing slash d. The curve slash c needs to be positive orientation, meaning that as you transfer slash c and the region should always be on your left. The region must be simply concerted, meaning it has no holes that would complicate the integral. Geometric interruption. Green's theorem can be visualized as relating the flow around the boundary of a region to the behavior inside that region. The left hand side of the equation represents the total circulation around the curve, whereas the right hand side representation the net outflow or inflow of vector field across the region. Applications in physics. Green's theorem is exclusively used in fluid dynamics in analyze flow fields. It can also be applied in electromagnetism, particularly in the context of electric and magnetic fields. Engineers are these Engineers use this theorem to simplify complex integrals in various applications such as stress analysis. Example problem setup. Consider field of y cap 2 x cap 2 and the curve C defined as a square with vertices 0, 0, 1, 0, 1, 1, 0, 1. To apply Green's theorem, we need to compute line integral around slash C and the double integral over square region slash D. This will demonstrate the equivalence of circulation around the curve. Evaluating the line integral. For the line integral point C p dx plus q dy, we evaluate its segment by segment around the square. Each segment contributes to the total circulation, which we will sum to get the total value. Each segment contributes to the total circulation, which we will sum to get the total value. This setup illustrates the direct application of Green's theorem to compute the integral. This setup illustrates the direct application of Green's theorem to compute the line integral. Evaluating the double integral. Next, we compute the double integral d left factorial partial x fractional partial p partial y right dA. For outer field math, we can find partial q partial x is equal to 2x. This integral will confirm the result obtained by the line integral around the curve C. Conclusion of example. Upon evaluating both integrals, we should find that they yield the same result, validating Green's theorem. This example illustrates the power of Green's theorem is simplifying complex problems in calculus. Understanding this theorem enhances our ability to analyze vector fields. Further readings and resources. For a deeper understanding, textbooks on vector calculus such as Manifolds by Michael Spivak are recommended. Online resources including video lectures and interactive stimulations can further clarify the concepts. Engaging with practice problems will solidify comprehensions and application of Green's theorem. in various contexts. Feel free to modify any of the context based on your specific needs or preferences. Thank you.